Welcome to lecture 27. So we continue our study about saturation and try to come up with some way to identify primes that have certain containment properties, and then we'll see some Macaulay 2 examples. And in the next lecture we will look at some ideas behind computing them, algorithmic computation of saturation. So in the last lecture, recall that if you I colon j saturation is the intersection of I colon ai saturation 1 through n, where j, so this is all in Noetherian rings and I and j are ideals, and this is j is generated by this n elements. This we saw last time. So if we want to find a way to saturate elements, it might be useful to understand saturating with respect to one element. Okay. So how large, okay, and we also know that, we also saw that also I colon a infinity is I colon a n for all n sufficiently large. Maybe you just, okay. So we saw these two observations, I mean these 2 points in the last lecture. And how large should this n be? Okay, so how large should n be? So I'll give one example which is relevant to these geometric discussions, but there are other ways one can understand this, and more will be in the some other variations of this will be there in the exercises. So let's prove one proposition in this. Okay. R Noetherian and I radical ideal. Okay. A inside R, then I colon a n is I colon a for every n greater than or equal to 1. So I will get saturated by a at the first step itself, okay, for a radical ideal. Okay. So proof. So this sort of an argument that we see in this proof is somewhat typical in arguing about colon ideals. So this should give you some familiarity to solve some of the related problems in the exercise. Okay. So we will first show that I colon a equals I colon a squared. Okay. So now what does I mean how does that follow? So let B be inside I colon, so first of all there is always one containment. Note that anything that multiplies a into I will also multiply a square into I, because I is an ideal. So I colon a is inside I colon a squared. Okay, so let B be inside I colon a squared. Okay. Then B a square is inside I, but I is an ideal, so B a squared is also inside I. Okay, so this is because I is an ideal. And this implies that BA is inside I. This is why I is its own radical. Okay, and which was what we wanted to prove, which is that B is inside I colon A. Okay. So now let's look at let B be inside I colon A to the m plus 1. This implies that B A m plus 1 is inside, sorry, let me take a different, once we have done the above argument, it's easier to argue it slightly different way. So what does that give us? So for every A, so what we have shown is for every A, I colon A is equal to I colon A squared. Now apply this to A squared, because that can also be done. So then we get that I colon A equals I colon A to the 2 to the k for every k greater than or equal to 1. Okay. Because if you do it with this, the square of A square will be A to the 4th, and square of that, and so on. Okay. And so we will go on like that. So we will get that there is this for an infinitely many exponents of A, I colon A to that exponent is I colon A. Okay. So now given any n, so let n be inside n, then there exists k such that, and let's say n is greater than or equal to 3, because 2 we have already taken care of, 2 to the k less than or equal to n less than or equal to 2 to the k plus 1. Okay. So then I colon A to the 2 to the k, anything that multiplies this will also multiply A to the n, and that will also multiply 2 to the k plus 1. But we know that all of these are equal to I colon A, and that is the okay. So this is I am not saying that going to this exponents of 2 is typical of these arguments, but these sort of manipulations that we look at some element, then try to manipulate and extract some more information from it, and so on. This is sort of okay, one has to do these sort of arguments in trying to understand these problems. Okay, so this proves one example, one case where one does not have to do a lot of saturation. The first colon itself gives us a saturation. So now let's go back to looking at associated primes proposition. So R Noetherian I and J ideals. Okay. P associated to R mod I colon J saturation. So I colon J infinity. Then P is associated to R mod I, and J is not a subset of P. Okay. So such P, I mean P that are associated to the saturation of the J saturation of I are associated to I and will not contain J. So this is a way of picking out certain associated primes. Okay. So by earlier proposition proof, okay, so by an earlier proposition we know what the saturation is. We just have to, this is just the intersection of saturation of individual a generating set. Okay. So let J be generated by n elements. By earlier proposition, by an earlier proposition, there have been many. The J saturation of I is the intersection of the AI saturations of I. Okay. And we have seen that if you have an intersection of finitely many ideals, so let's write it here. If you have an intersection of finitely many ideals, okay, this injects R linearly to the direct sum of those quotients. Okay. But this is just R mod I colon J saturation. Okay. So we have, this is maybe, yeah, this is, we have R linear maps. This is an isomorphism or equality because these ideals are the same, and this is an inclusion map. Okay. P is associated to this, so R mod P injects into this, so it injects into this, and if it has to inject into one of those things, it must be associated to one of those elements. Okay. Because the associated primes of this is the, right, so this we saw associated, so therefore P is associated to the direct sum of these modules. Okay. And if you have a direct sum of modules, then the associated primes are the individual, the union of the individual associated primes. Okay. 1, and therefore P is associated to one of them. So without loss of generality, P is associated to R modulo I colon A1 saturation. P is associated to. Okay. So we can replace J by a principal ideal, so without loss of generality. We just have to prove that A1 is not inside. So let's, okay. So what we, okay. So if we show the theorem for a principal ideal, then A1 will not be inside P and hence J will not be inside P. Okay. So enough to show that P is associated to R mod I and A1 is not inside P. That would be proof for J also. So without loss of generality, J itself is a principal ideal generated by one element. Okay. So instead of calling it A1, we'll just call it A. Okay. So then, so we want to show that P is associated to R mod I and A is not inside P. Okay. Let's again, this is sort of the usual, again a rehash of various arguments that we have used earlier. So let M be such that the saturation is the mth colon up to the mth power. Okay. Then arguing as earlier again, note R mod I colon an I colon a m injects into R mod I, and the quotient is I plus a to the m. That's not relevant for us now. And P is associated to this. R mod P is associated to this. So I mean R mod P injects into this. So therefore P is associated to R mod I. Okay. So we prove the first part. We want to prove the second part now, which is A is not in P. Okay. So by way of contradiction, assume A is inside P. Okay. Note that there exists some x not in I such that the annihilator of x in R mod I, which is the same thing as annihilator of x in R mod I, thought of as an R module, so which is the same thing as I colon x, is equal to P. Sorry, I apologize, I made a mistake here. Sorry, there exists, so P is associated to, the assumption is that P is associated to R mod I colon a to the m. Okay, we don't need to use this conclusion, just use this, I mean, start from there itself. There exists an x such not inside I colon a to the m such that P is the annihilator of annihilator in R of X. I mean X, maybe I should just say P multiply, P is what takes X into this ideal. So I colon AM colon X. Okay. But what does this say? So, but what is I colon M colon X? This is just I colon AM colon X is just I colon AM X. This is a property about colon ideals, which not just principal ideals here, any ideal which you will work out in the exercises. So we have this P is I colon A to the mx, but we assumed that we have assumed that A is inside P, so which now implies from here that A to the m times x is inside I times x is inside I. A to the m plus, sorry, A times A to the m, sorry, A is inside P, P multiplies A to the mx into I. So A times this quantity is inside I, that's what I wrote here. Okay. So in other words, x is inside I colon A to the m plus 1. Okay. But where did we pick x? X was not inside I colon m. Okay. But this now implies that I colon m plus 1, sorry, I colon am plus 1 is strictly bigger than I colon am, which is a contradiction because this was a stable value. And the contradiction came because of this assumption. Contradiction came because of this assumption. This assumption here. So therefore A is not inside P. Okay? So that's the end of this proof. So this gives us a way to construct, to sort of incrementally determine associated primes of an ideal by sort of looking at saturations. Okay, so one more proposition. This is mostly of some geometric, trying to reinterpret all these things in terms of the geometry coming from Nullstellensatz. Again, R Noetherian, I and J ideals. Then V of J colon, I colon J saturation is V of I minus V of J closure. Okay. So this is not entirely surprising given this proposition that by saturating out J, we have removed associated primes that contain J. So this is not really surprising that we have removed some part of V of I. And so I have written this in terms of an arbitrary Noetherian ring, but one can specialize the same situation where we take R to be a polynomial ring over an algebraically closed field, and instead of writing V here, we can write Z and prove the same statement. Okay, so that's not difficult. Okay, so proof. So we will prove that left hand side is inside right, the two inclusions. Okay, so this containment, left is inside right, other way around, sorry, this containment. So let's take a P that is inside here. Okay. So let, not inside here, because remember this is a closure of some set. This is a closure in Zariski topology. So this is closure in Zariski topology. Okay. So if you take an element inside here and then forget the closure, just the Vi minus Vj, then if you show that is inside the set, this is closed, so its closure is inside here. So that's all we will need to prove. So let P be inside V of I, but not in V of j. Okay. So let A be inside J, but not in P. Okay. So now we'll try to saturate this element. Let B be inside I, but Jm, some m. So B A to the m, A to the m is inside here, is inside I. Okay. But A to the m is not inside P, so B is inside P. A is not inside P, so this says B is in P. Okay, so what is the conclusion? We chose an element B that is inside I m. Okay, so this one says that I colon j to the m is inside P. P was chosen here. Okay, for every m. So I colon j saturation. I mean j saturation of I is inside P, and that's exactly the statement. Okay, so therefore P is inside V of I, j saturation of I. Okay, since V of an ideal is always closed, we see that Vi, so what we just showed is Vi minus Vj is inside this thing, so its closure is also inside. Okay. So this is one direction. Right side is inside the left side. Yeah. Okay. So now the other direction. Okay. So now let's take a prime containing this. So let P be a prime ideal such that P contains I colon j saturation. Okay. So what does that mean? It means that there should be a minimal prime containing this, which contains I colon j. So this implies, so let Q be a minimal prime over this I colon j, okay, such that P contains Q. P is some prime ideal containing this, therefore there must be a minimal prime containing this which is inside P. So let's take Q. Such a Q is associated to R mod I colon j saturation. Every minimal prime is associated. Okay. But this implies now that Q is associated to R mod I, and of course j is not inside Q. Okay. So this is j is not inside Q. Okay. This is by the previous proposition. Okay. But now what is P? So P is inside, okay, V of Q. That's because P is a prime ideal containing Q. But how do we, I mean, what do we know about, yeah, so let's see. So maybe before I just, or maybe I can, okay, so P is in V of Q, but what is V of Q in terms of a closure operation? It is the closure of the singleton set just containing Q. That is because this just definition means all prime ideals containing Q. Okay, so this is V of Q is a closed set and it is the closure of this singleton set. but this is inside, so Q is inside V of I and Q is not inside V of J. Okay, so this Q, the set containing Q is a subset of V of I minus V of J, and its closure therefore is inside here also, and that is what we wanted to prove. A P that was in V of I, an arbitrary P that contained I colon J saturation is inside this. Okay. So one can also rephrase this to study irreducible components of varieties inside Kn, but that would be just restating this the same. Okay. Okay. So, so we'll do a quick example about saturation going from the previous, in one of the earlier lectures. We'll do it in Macaulay more thoroughly, what we did by hand. And then we'll do a much more, slightly more elaborate example in the next lecture. Okay. So this is the example from from an earlier lecture. Okay. So as so we have a polynomial ring so ignore these lines. Polynomial ring in 4 variables u, v, x, y, same thing as what we were discussing last time. Ideal in this, the output is, it says it's an ideal. So these lines are output, the offset lines are input. Okay, so then we ask for I colon u. Okay, so then it says x, y squared. So it would have in some way calculated. We will discuss how these things are calculated in the next lecture, okay, or maybe after that. And so it just calculates this. It says x is there, yeah, x is there, and if x is there, then y should be there, uy should be there. Okay, so it saturates this one. Before we saturate, we just I colon u. Okay, so if we do I colon u, we get this thing. So there's still a u, so this is not the saturation. So let's do it I colon u squared. Okay, so I colon u squared here. Okay, and then we get this output which is y comma x, ideal of R. Okay, so now let's see. So x comma y is a prime ideal of R, and if Rz is in x comma y, sorry, that should be R times u. Ru is inside x comma y, it would say that R itself is in x comma y for every R in R. So after this, I colon u to the m will be inside I colon u, it will be just I colon u squared for every larger m. So that is the saturation. Okay. So this is one way of taking these colons successively and figuring out when it stabilizes. In small examples we can do, and this is what we did. Okay. We could also just give the Macaulay 2 command called saturate, and so this is what we did here. Okay, so we just asked you to saturate with respect to all 4 variables, and here is the output. Saturation with respect to u, saturation with respect to v, saturation with respect to x, and then y, as expected. So this is what. Okay. So now, with the stuff that we have studied, okay, the primary and some exercises, the primary component of I corresponding to x comma y is the same as that of I colon u saturation. Okay. So therefore, the components, the primary components corresponding to the minimal primes are x comma y and u comma v. Okay, so this part requires you to do some exercise which says that not just the associated primes, but the primary components themselves are preserved. The same relation would be there for when you do saturation. Okay, so after that exercise, this will be clear. Okay, and then we ask to intersect the ideal x comma y and u comma v. Then we ask, is it same as I? And Macaulay says no. Okay. So which means that there must be a non-minimal associated prime, what is called an embedded prime. Okay. But let's see what the calculation says. Calculation says there's only one associated prime that does not contain there's only one associated prime that there's only one associated prime that doesn't contain u, which is y comma x. Similarly for v, just y comma x. Okay, so every other associated prime other than these two must contain all the 4 variables, which is what we ask, we conclude here. There must be an embedded prime which must contain all the 4 variables, but once it contains all the 4 variables, it's a maximal ideal, and therefore it must be a prime associated prime. There's nothing bigger. Okay, so then we just so this is code which I will type this line in the exercises. It has gone outside, so I'll type this in the exercises. Apply so we're running a apply command which is from elements of this list. So to list 1.5 means construct a list which elements 1, 2, 3, 4, 5. So take 1, 2, 3, 4, 5, and to k we ask this question: is I equal to something here? Okay. The something here is intersection of u comma v, x comma y, and a third ideal which is I plus the ideal of all the variables to the kth power. Sorry, that's gone outside this file. So I will describe this example in the exercises again. So what we take is I plus this ideal to the kth power. That's what this expression is. And then we ask whether I is equal to this intersection, and for the first 2 values 1 and 2 the answer is false, and 3rd, 4th and 5th onwards it is true. And what we so this is what I have written: for k greater than or equal to 3, I is u intersect v intersect x comma y intersect I plus the variables to the k, the ideal generated by the variables to the kth power. This is a prime ideal, this is a prime ideal with different associated primes, and this is a primary to the maximal ideal, so this is also primary, and hence this is a primary decomposition of k. And we did this example by hand earlier, and it shows that primary decomposition is, except for the minimal primes, this is very non-unique. So we will stop here. We will discuss the next example in the next lecture.